Hey guys, welcome back. We're talking about reaction mechanisms in this one. And this is the how the reactions happen, right? It's the actual making and breaking of chemical bonds. So it's the sequence of making and breaking chemical bonds, which is also the rearrangement of atoms. I always like to start this off with like just putting your socks and shoes on. If you're going to give somebody directions how to put socks and shoes on, what do you say, right? And all right, we just now usually we say, "Hey, put your socks and shoes on," right? Or somebody tells you, "Put your socks and shoes on," or whatnot. But if you're gonna do the socks and shoes, do you put your socks on first, then the shoes? Are you a shoe person? Are you a sock shoe person? But you're definitely not a shoe sock person, right? And so the order matters, right? And whatnot. And maybe you are always the left foot first or right foot first. Maybe you've never even thought about it. Now I'm going to mess you up. I don't know, right? But when you put your socks and shoes on, there's a sequence of steps that you have to follow, right? Okay, so maybe, and a lot of times athletes have these superstitions where they put a certain sock on, then the next sock on, then the next shoe, then the next shoe, then they tie. Or maybe you put all of one on, a whole left shoe on first, left sock, shoe, tie it, then the right sock, right? Whatever you do, right? You have a sequence of putting your shoes on. Not much different here with chemical reactions. There's a sequence of how reactants interact, how they collide, and then that collision results in another. Maybe it's the final product, maybe it's intermediate. All right. And so we're going to dive into like how we describe this and how we visualize it, because what really happens may be or may not be what we think, right? Because we don't actually see the individual atoms. And so we have some pretty good things. We can cool things down and see that there are some intermediates that we form and whatnot. But, it's how we think about this really helps in how we predict behavior. Again, most of the science is how we predict behavior. So let's dive in. So the reaction can occur in a single step, right? There are some reactions, like especially a decomposition reaction, like hydrogen peroxide decomposition. That's just a single step, one step, boom, done. But it can also occur in a sequence of steps. So each step is characterized by its molecularity. And so if it's one molecule, it's unimolecular. Two molecules colliding, it's bimolecular. Three molecules colliding, it's termomolecular. So each step of the reaction is an elementary step. Now, we can write the stoichiometry or the rate law based on the stoichiometry of the elementary step. That's what we actually do, not the overall reaction. So it doesn't matter what the overall reaction is, it's stoichiometry of the elementary step. Now, the slowest step is the rate determining step. All right. So if there was an Olympic or even a college, a university, your local university's sprinting team, right? And so they had each person's going to run 100 meters. So that would be the 4x100 meter sprint. And so if you have me starting out and then three other people, right? And we're doing the 4x100 sprint, we're probably not going to win. And I would be the rate determining factor there because I would be the slowest one in my old age. You replace me, and now the team has a better shot of winning. Okay? And so the slow step is the rate determining step. Now, something that's very important with these mechanisms is that the mechanism is what we're proposing must agree with the experiment, the experimentally determined rate law, right? So the experiment, what we observed through experiment, our proposed mechanism must match the experiment, okay? Now, when we do these, when they have these sequence of bond breaking, bond making, you can have intermediates, which are produced in the reaction and then consumed. Going back to the example with your socks and shoes, right? If you have a sock on both feet, that's intermediate. You're in the intermediate stage. If you have your socks and shoes on, not tied, intermediate. All right. And so what we see when we see reactants go into products, we're now talking about this arrow. All right. So intermediates are produced and then consumed. And they're not in the rate law. They can't be in the rate law because we can't control their reaction directly. All right. Catalysts, we've already talked about what those do, right? Catalysts, they're consumed in the reaction sometimes and then reproduced, right? And they can be in the rate law because we can control how much catalyst is there. All right, so if we look at some examples here, right? A going to products, that's a simple decomposition, unimolecular, there's your rate law. And if you want to put a 1 there, you could, you don't have to. So by two bimoleculars, where you had two A's colliding, right? The rate would be Ka squared. Or A and B colliding, it's still bimolecular, and rate would be A times B. So it's first order with respect to A, first order with respect to B, but second order overall. In a termomolecular, where you have two A and B colliding to make the products, right? You have rate equals Ka squared times B. So that's kind of how this is going on. Now, let's do some examples to kind of make this better for ourselves. All right. First example, I have a proposed mechanism of N2O with the first rate constant, all right? And we got N2 and O2, and the step 2 would be N2O plus O going to N2 and O2. All right, let's get to all the things. It says the experimentally determined rate law is rate is K-N2O. What's the overall reaction? Well, overall reaction is pretty straightforward. We can just add these up. All right, if I add these up, we would have N2O, and I would actually have two of those, plus O going to 2N2 plus O2 plus O. And you might notice that this O is canceled. So the overall reaction would be 2N2O going to, or producing, 2N2 plus O2. All right? And so that means this O is an intermediate. All right? And that's actually the question number 3. Right, so if you look, the intermediate is produced in step 1, and then it's consumed in step 2. So that's the intermediate. This would be the overall reaction. Which step is slow? Well, the rate law comes from the slow step. And so if we had to rate the rate law of each of these, this step 1 we rate is K1 times concentration of N2O, which matches our rate law. So the slow step would be 1. Right? Step 2, the rate would equal K2 times concentration of N2O times the concentration of O, which we cannot have the concentration of O because that's an intermediate. And so our proposed mechanism supports, right, or the rate law would support this mechanism, and the step 1 would be the slow step. All right, so there's the first example. Second one, hydrogen peroxide decomposition with iodide catalyst. The rate law is rate equals K times concentration of hydrogen peroxide times iodide. Propose a mechanism. All right, so we have H2O2, two of them, going to 2H2O plus O2. And we have a catalyst of I minus. So there's my catalyst. All right. And so chances are, step 1, I'm going to have H2O2 meet up with I minus. All right. And so if we do that for step 1, what could be the result? All right. That's the question, right? And so I'm going to draw draw this here. All right. So what could happen? I don't know, right? And so could we just add H2O2I? Probably not, because I minus, right? I minus here really has all its electrons, right? So if we look at I minus, right, it's got its electrons. Iodine can actually gain, right, an atom, but oxygen can't gain any more electrons, and hydrogen is not going to. Well, so maybe, an option, and then if we do this is K1. Maybe it could be H2O, which is one of the products, plus then, right, IO minus. Maybe that would be an option. All right. Step 2. We would have now what? We would need another H2O2 reacting with our IO minus, going to H2O again. And then what else would we get? Well, maybe we would get IO2, which maybe we would just get O2 and I minus. Maybe we'll do that. And so I minus is, I'll put that in purple for a catalyst. Then we're going to highlight this one. All right. And would this work? Well, if I add them up, I get our reaction. All right. We have an intermediate here. And so this mechanism would work as a proposed mechanism for the decomposition of hydrogen peroxide with iodine. All right. Now, how do you know for sure it's right? Well, it agrees with the rate law. It works. All right. Now, there are experiments we could do, and if we could actually see one of these intermediates, then great. But otherwise, we're just proposing a mechanism that is consistent with the rate law, which we did. All right. Another one. 2NO plus Cl2 going to NOCl and gives you the rate law. Propose a mechanism. All right. Well, in the slow step, we know the slow step NO and Cl get together, and they can do that. So in step 1, I can have NO plus Cl2 getting together. All right. And, oh, I have a typo here. That should be a 2. What comes on the other side? Well, I can make what? Maybe make a product. NOCl plus Cl. And then step 2, all right, we have what? Another NO coming plus Cl, our intermediate. And if we do that, I'll have to make the arrow. If we do that, we can get another NOCl. And so this would be slow. This step 2 would be fast. If we add these two up, right, my intermediate here is gone. I would have 2 products, which I'd have 2 products. I'd have 2 NOs, nitrogen monoxides, and a Cl2. So that would be a consistent mechanism with the rate law. All right. One more example. And this is the hard example. Mechanisms with fast initial steps. All right. And so I want to know if this mechanism is consistent with the rate law, and it gives you the reaction here and the rate law. All right, so if you notice, I have fast, slow, fast, and I have a fast reversible step. All right, so I'm going to write down if the first step is fast and a reversible reaction, which it is, all right, according to our proposed mechanism, we can assume that the concentration of chloride, Cl, of chlorine, elemental chlorine, is maintained and this is called the steady state approximation. All right, and why do we do that? Well, once we get equilibrium going, all right, the concentrations of chlorine gas and the 2Cl are going to be consistent with time, right? They're going to be in equilibrium. So once equilibrium is reached, we should have a pretty steady state concentration of Cl. All right, so how does this work? Well, the slow step is where the rate law needs to come from. So this is step 2. Rate equals the concentration of Cl times the concentration of CH3Cl. Now I forgot the K. You got to put it in there, K2. All right. So that would be the slow step. Now, step 1, I want to point something out. Step 1, we have rate would be K1 times concentration of Cl2. And then we'd also have the rate K negative 1 concentration of Cl squared. All right? And we're going to say at equilibrium, these equal each other. Okay? All right, because the rate forward equals the rate reverse, or the rate back. All right? So that means I'm coming down here, I'm going to say K2 times the concentration of Cl2 would equal K minus 1, okay, minus 1, times concentration of Cl squared. All right, well, let's separate, well, what do I want to get by itself? I want to get Cl by itself. So then I divide both sides by K negative 1. So that means I would have K2 times concentration of Cl2 divided by K negative 1 equals Cl squared. All right, so now I gotta get rid of the square root, right? So we get rid of the square root. The concentration of Cl would equal the square root of K2 K2 concentration of Cl2 all over K negative 1. Well, I'm going to rewrite that as the concentration of Cl is going to be equal to the square root of K2, K1, times concentration of Cl2 to the 1/2 power. All right. Now, I'm going to substitute all this in my rate constant. So we're going to come down here, and we're going to substitute Cl in. We're going to substitute that, right? That's Cl there. I'm going to take all of this, and put it in for Cl. So let's look at that. Rate equals K2 times the square root of K2 over K1, K negative 1, excuse me, K negative 1, all right, times concentration of Cl to the 1/2, and we still have CH3Cl. Well, now, we can only measure one rate constant. So if that's the case, that just becomes K, right? So we get rate equals K, our rate constant, times concentration of Cl to the 1/2 times the concentration of CH3Cl. And that is our experimentally determined rate law. So that's how these mechanisms with these fast initial steps work. You got to do some algebra with the rate constants. All right, so hopefully that works with the rate laws and the rate reaction mechanisms. Feel free to reach out if you have any questions. Otherwise, guys, we'll see you next time. Take care.